Well, this lesson is on the parameterization of a space curve. So as I mentioned in my first discussion of multivariable functions, we have the example of a line, but it's in free space. So it can have a shape that's complicated, shall we say. But it can exist in 3 dimensions. Yet the only choice you have about direction is which way you go along this pathway. And hence we call these things space curves. Now, to deal with the x, y, z coordinates of this line independently would be quite a difficult in comparison calculation. But if we recognize that we simply slide along this line, and our location on that line can be described by a single variable, and that we call a parameter. So let's look at first and see what we do in high school in the non-AP world. You might have the following. And so you could have a line that would look like this, and might describe it this way. We have vector 1, 2, 3 plus some parameter times 3, 4, 2. And so this is in effect a y equals mx plus b version in R3. But the line is straight. And so what happens now is we'll deal with the situation where the line is curved, and how this allows us to make some very interesting calculations along these lines. Pun intended. Very well. So we know a space curve is a mapping of R to R3. My goodness, folks, pardon me. Yeah, no, that's right. Okay? So we have a single variable argument, and it gives us a 3-dimensional coordinate. Let us recast this so that everything is based on a single variable. Now, we know that this line is going through some free space, so we're not basing on x, y, and z. Let's be based on an arbitrary variable, okay? So, emphasize here, not. Now, that's not to say that this parameter can't agree with x or y or z, but we want to hang our hat on that, okay? So, not x, y, or z. Let us define t as a parameter. And so for the physics folks out there, note in this instance t is not time. Okay? I know that's a bit hard. I mean, you can listen to me, but to internalize that, you need to think about it a little. Okay, whereas this is math circumstance, maybe if we're doing a physics application that has time as a variable, we might choose a different value, but this is typical, and we'll go with it for now. Our space curve and in our example can be R2 or R3. So we can have an interesting curve in 2D and treat it the same way. Or of course, as we already spoke about in R3. we will use a lowercase sigma as our function symbol. So in that case then, sigma of t will equal sigma x of t, sigma y of t, and sigma z of t. Okay, and these equations are known as parametric equations. And so let's look at some examples. We'll start off, and then I'll show you kind of where this gets really interesting. So let's suppose we take a circle. So in R2, of circle. Now, the way that you've considered the equation of the circle in the past is a bit different. And what we're going to do here is think of the line itself and its coordinates. So we would have sigma of t is equal to, and we can have, we'll just take a radius of 1 here just to keep the math simple because it doesn't really make a difference anyway. Okay? So now we can choose our coordinate here, which would be a function of the angle. Okay? So we could say cos t, sine of t. So our parameter is not an x and it's not a y. It's the angle in radians. So if we want to power 2, so we could have different arguments here. So this thing ranges from 0 to 2 pi. And you will get all the points that describe that circle. We can do it out of parabola, which is probably more use to the students. So in high school, you'll see y is equal to x squared. Okay? That's how you've always seen a parabola. Okay? But in parameterization, this doesn't help us very much with what we're trying to do here. So in parameterization, sigma of t is equal to quantity t comma t squared. In this case, by coincidence, x and t are identical. They don't have to be, but they are in this case. And so this is these are the parametric equations for your parabola. Okay, basically x and x squared, as you already know. Now, why do we do this? Well, I think there's a little bit of a point initially. You can say, well, this does make it a bit easier to describe certain functions. But here's what makes it interesting is, what if we want to learn about the properties of these things? So, for example, arc length. In a circle, it's easy. So we're not going to have to use fancy techniques to get the arc length of a circle. We know it's simply the radius times the angle in radians. Okay? That's how radians are defined. So that's not a big deal. But if we deal with other shapes, this is less so. So let's consider the example I would use. And you've studied. So compute the length of y equals x squared, x equals 1 to x equals 3. Now let's understand what I'm asking here. Okay? So here's the parabolic function, and we have 1 here, and let's say 3 here. I'm asking you to calculate the actual length of this line in profile. Okay? Now, that's something you've never done before, in most cases, and certainly not in high school. And such calculations are necessary for lots of situations. And this is, of course, a parabola, so that the curve, its radius, etc., is constantly changing. So let's see what we can do with this. One of the challenges with calculus is that the idea that we're trying to do is often fairly simple. And the idea that we're doing here would be the same regardless of the function. The big picture idea doesn't change. But the difficulty in computing the answer can be vastly different. And so one of the challenges that you face in calculus is that a lot of the integrals that you're going to compute or whatever are going to be difficult. And many of them don't exist algebraically. And you'll have to compute them on a computer or use the fundamental theorem of calculus or something like that. And so as a consequence, you'll find in your calculus studies that after learning 3 or 4 courses of calculus and getting some background, you'll now then turn around and take 3 or 4 computer courses to learn how to do this on a computer. Now, obviously I went to university 25, 30 years ago, and things have changed, but the conceptualizations are still legitimate. And the training that you endure, even if those types of those platforms exist already, you still need to learn about them to understand them. Because if we think about today when we're modeling the surface of a submarine or the aerodynamic properties of an airfoil or what have you, okay, we're solving simultaneously, literally hundreds, if not millions, of differential equations at the same time. Now, it's not that humans are going to do that. The machine does that, but we have to understand how the machine is doing it. We have to make darn sure that there isn't something wrong in the algorithm, because that could lead to a disappointment in our results. Anyhow, back to this comparatively simple world here. Let's look at it microscopically first. So now we have a little triangle. So, and this is going to be ds, dy, and dx. And my function, my parabola here, this is a microscopic piece right here somewhere. Okay? Can't see it with the eye. However, it is not infinitesimal either. And we can see by Pythagoras that we get ds squared equals dx squared plus dy squared. And furthermore, were we to do it, ds then is the square root of these two. Okay? Now here's the point. If we want to, I just want to make sure we know what we're trying to do here. We want to find out this arc length here, then we need to add up all the ds's in this interval. So we need to find the arc length. We need to sum all the ds's from x equals 1. And that's what we're trying to do here. So our parametric equations, we have sigma t is equal to t comma t squared. Okay? And so what we're going to try and do here is we want to express these variables in terms of t. And then we're going to look at how this variable changes with respect to t. So let's have a look and see what we get. quantity dx dt squared plus dy dt quantity squared. And we can separate if we want to. And then a dt in the back here. Now, let's look and see what we have here. So, the x dt is equal to 1 because our x variable is t, our parameter. Just happens to coincidence in this case. So, the d dt is going to be 1, and dy dt is 2t. And so now we can say ds is equal to the square root of 1 plus 2t quantity dt. And when we write it this way, this equation is separated. All the s's are on this side, all the t's are on this side. Now, one of the cool things about calculus, when you've done the fundamental theorem of algebra, you know if you multiply by 3 on the left-hand side, you multiply by 3 on the right-hand side, and you lose your equality. In the case of calculus, it's a bit different because if we integrate, as long as this equation is equal in this manner, we integrate this side with respect to s, and this side with respect to t, and the equality is preserved. And so this is what we've known as separation of variables. And in many ways, when you're integrating in your first calculus course, that's all you're doing. And of course, as you'll see soon enough, any equation that has a differential in it is a differential equation. The simplest versions are just your basic integrals. And you solve those equations, as you'll see, by just direct integration. And so we don't really think about them as differential equations until we get to more difficult ones. But that's for another lecture. Okay. So now we have an expression for ds. So let's see what we have to do now. So the length of our arc is equal to the integral of ds, which is equal to the integral of the square root of 1 plus 2t dt. And now we have to also put in our limits of integration. Okay? Now we're lucky in this case that t is equal to x. Okay? So t specific limits of integration. And so here we would have then L being equal to the integral from 1 to 3 of the square root, and I did something wrong here, didn't I? I didn't square it, did I? I had to square my dy dt, so this becomes 4t squared. It's not enough to rub the words off, so we'll just fix it. 4t squared, okay? And we have 1 plus 4t squared and dt. So I want to put a star here, okay? So the limits of integration are t specific. I know I just wrote it above here, but I'm saying it again, okay? It is just a coincidence that t equals x. So I'll say to you, make a note in your notes as you look at this, one of the mistakes that students will make in arc length computations, you get everywhere, you get to here, you'll be fine. And then you'll forget, and you'll make these x's instead of t's. So you're going to have to look at what you've got there. So you saw, for example, when I did the circle. I'll go to that. Okay, when I did the circle, and I've got cos t and sine t, right? And so now I want to find the arc length between here and here. Okay, I've got to think about what t is there, not x and y. And so that's pretty important. Now we will avail ourselves of an algebra engine. And so then you have 1/2 absolute value, square root of 1 plus 4t squared, plus 1/2, 1, plus the square root of 1 plus 4t squared, end of absolute value. Now we go through the math on this. You're smart enough to do that. So with 3 dots, or 4 dots now, you'll get 8.26 units, 68 units. Okay? And if you did straight Pythagorean theorem, you'll get a different number because you're cutting the corner. Okay, so you can substitute in here, and this will be 3 to 1 and stuff like that. And you do it. That's not so big. You don't need me for that. Now, here is another thing. Observe that the following. So L is equal to the integral of the norm of this. So we don't have to remember all of this. We don't have to go through all this laborious calculation because we've already made the definitions here. So remember, this is the norm or magnitude of sigma prime of t. And this is the 2 norm, of course, as we do it here. And so this would mean sigma prime of t is simply going to equal the square root of 1 plus 4t squared. And how do I know that? Well, because sigma prime, this is sigma, the prime of that will be 1 comma 2t. Okay? Now we're going to take the norm of it. The norm of it is simply just this Pythagorean example. So we're going to do, you know, the length of a line, okay, x squared plus y squared square root. Same story. So we're just doing exactly what these definitions give us. And that's how we can, this gives us arc length. And then I'm going to put here on the integration, we've got t initial and t final. Okay? And again, if I can't stress it enough, because if we make a goof on a test where you're doing okay, and you've done your homework, but this is the kind of thing where you can blow a mark or 2 just because you forget to convert. So thought I'd say 4 times down, just to help you out. Okay, one more idea in this section before we pull the plug here. Because we've only done sort of half of it. So we can extend our ideas from last year. In grade 11, we found that the work is defined as, so we had work equal to first integral of f ds, which is fine, but vectorially, because this is assuming 1d, right? So then vectorially we'd have work is equal to the integral of f dot ds. So let's see what that means. So perhaps the question we should ask first is, so wouldn't it be nice to compute the work done by some f? Let's say, some R3 variable f on a R3 space curve. So there's a litmus test for you. Now let's see what we can do here. We know we have a dot product to compute, and we also know something else. So f is typically f at x, y, z. So for the space curve, we want f of t. And what we do is we do f of sigma of t. Because f is in R3, and sigma is R3, sorry, is R to R3. So by putting a sigma inside here, we satisfy the requirement for a three-dimensional input. But that collapses then to produce f of t, which is what we really want. We want the force. We only care in this computation about the force along this thing, not the force over here or there or somewhere else, but just along whatever this is doing. And so now we want to be able to compute the two, and we know we have to dot them because that's the rules. So we get the work equal to the integral of f of sigma of t dotted with sigma prime of t dt. Now the nice part about doing this way is that if we do the parameterization, this entire integral now is one variable, something that you're experts in. So this is an integral of one variable. And in comparison, that is a good thing. All right, so let's just have a little bit of sport here, and we'll just do it in 2D. So we'll keep our parabola here, t plus t squared. And our force, we have sigma prime of t is equal to 1, 2t. And my force vector will be a coward today. And I think I'm gonna try a little harder than this. So we'll have x comma 2y. So this is second here. So my force of xy is equal to x comma 2y. Okay? Let's just suppose that's what it is. So we have our sigma of t. We're going to drop it in now. So this is going to give us f of sigma of t is going to be equal to, so this is going to be t. So this is what drops in here, okay? So this is here. So we're going to end up with t comma 2t squared, okay? That will be our force at any t along that curved path. Now, we already know the sigma prime of t, we've done that one, okay? So our integrand is going to be f of sigma of t dotted with sigma prime of t. So let's see what that looks like. So we're going to have t comma 2t squared dotted with 1 plus 1 comma 2t. And now we'll have, so when we're finished, we're going to have t plus 4t cubed as our integrand. And then the final computation to compute the work, and we already had we're using the same example here anyway. is the following, where we have the work now equals the integral from 1 to 3 of t plus 4t cubed dt. And you don't need me for that, it's just a reverse power rule. Okay, and you're all done. So the nice part about all of this is that we can then compute these integrands and this work through this single variable calculus, even though we're operating in a 3D universe. Because we could then say, well, what's the work somewhere else? Because this, ultimately, of course, the work would be equal to the work as a function of t. So then you can choose a location on the loop, say how much work's been done from here to there. So we could be partway in between or somewhere like this, and it'll tell you. Okay? So it's a pretty powerful method. And we'll do a bit of that in our work this year as well. Now I've done all of the earlier examples that I gave you with respect to inertial frames and things like that. But before I want to go on to the second phase of the math preparation before I start into applications, and that will be the study of differential equations, which is will be the next video. Thank you for watching, and if you've enjoyed this information is useful to you, please consider subscribing and tell a friend. Thank you very much.